let us recall what we have discussed in the last class. So we discussed Taylor series expansion and then after the Laurent series expansion, right? So the question is, given a function, how to find its expansion in the entire region? Or if you can't write the expansion in the entire region, you can divide the region into parts, and each subpart, what will be the expansion? What is the possible expansion? So for example, if you look at 1 by z, and I would like to express this summation centered at 1, z minus 1 whole power n. So we know that it is possible to express this summation when r equal to 1 only, when the radius is 1. So if you go beyond 1, what is the expansion? So you know the region in one region. Sorry, you know the expansion in one region. So what is the expansion in the other region? For example, you can see 1 by 1 minus z. When mod z is less than 1, you know this is the expansion, summation z power n. When mod z is greater than 1, the expansion is going to be summation minus 1 by z power n plus 1. So this will be the expansion when mod z is greater than 1. Okay. And here is a Larn theorem which says that if you have a function which is analytic in this annular region, and this annular region is centered at z0, and if you want to express f of z in terms of power series which is centered at z0, and you know here it is going to have these terms as well, 1 by z minus z0 whole power n. Okay, so when you write an expansion of this kind, then definitely an can be found using this formula, whereas bn can be found using this formula. That is an equal to this and bn equal to 1 by 2 pi I into integral along this c, where c is any closed curve in the annular region which is created around z0. Okay, I am not allowed to work along this curve. So I should work along a curve in which z0 is there. Okay. So you can look at the formula for bn, 1 by 2 pi I into integral f of z by z minus z0 whole power negative n plus 1 into dz. This is what. And we see some possible expansions. For example, f of z equal to sine z by z power 4. We'd like to write its Laurent series expansion about z equal to 0. We saw that the series expansion is nothing but this, 1 by z cube minus 1 by 3 factorial into 1 by z plus and so on. Okay, so in the Laurent series expansion, the first part we call analytic part, right? So this one, we have infinitely many terms in the analytic part, whereas in the other part, so we have only finitely many terms. So the highest power of 1 by z is 3. That is 1 by z power 3. Okay. And next, so we have seen expansion of 1 by z plus 5 about z equal to 0. So when mod z less than 5, we have seen the expansion. I hope we have seen the other way as well, when mod z is greater than 5. Okay. And at the end, I asked you to work on it. F of z equal to 1 by z minus 1 into z minus 2. So you need to give me Laurent series expansion, all possible Laurent series expansions of this function about z equal to 0. I hope these three you must have done. 1 by z minus 3 sine z by z cos z by z power 4. You must have done this, right? Now let me discuss about this guy, f of z equal to 1 by z minus 1 into z minus 2. So the problem is f of z equal to 1 by z minus 1 into z minus 2. So we need to find Laurent series expansion. About 0. So we need to find all possible Laurent series expansion. Okay. So since they are asking about 0, first let me see where are the singularities of this function. So the center is 0 because we would like to find a series expansion about 0 only. And the singularities are z equal to 1, that is one singularity, and z equal to 2, this is another singularity. So now if you draw a circle centered at 0 up to the nearest singularity, so this is 1. Okay, so in this region we can have Taylor series expansion of the function. When mod z is strictly less than 1, we can have a Taylor series expansion. It means you do not have these terms 1 by z power k. So you'll have only z power k, these type of terms only. We'll have a Taylor series expansion. But whereas in the second region, that is in between 1 and 2. So let me draw that region. So when you are in between 1 and 2, let me call this region as R1. So now here R1 is the region which represents the region between these two circles, 1 less than or equal to, or 1 strictly less than mod z less than 2. See, you can see this circle is nothing but mod z equal to 2. Whereas this circle, it is centered at 0 with radius 1, so mod z equal to 1. Okay, you are exactly taking the region between 1 mod z equal to 1 and mod z equal to 2. So that's what I have written. Okay, so here, so we will not fully have Taylor series expansion. Okay, so if you observe that in this region, you can see mod z is less than 2. So maybe for this guy, you're going to have Taylor's, and whereas for the other, you'll have the Larn series expansion. So the next, the region outside this big circle. So that you can write it as mod z greater than or equal to 2. Or we don't include the boundary, so we simply take open sets only. So now let me write R3, R2, which is nothing but mod z greater than or equal to strictly greater than 2. And initial region R0, which is mod z strictly less than 1. So we have these three regions. So in these three regions, we need to obtain series expansion. Okay, so first let me work with the first expansion, first region R0, that is what mod z is strictly less than 1. So you start with the function f of z, which is 1 by z minus 1 into z minus 2. So it is good to take partial fractions here. So the partial fractions are 1 by z minus 2 minus of 1 by z minus 1. You can check that when you take LCM and cancel out the numerator things, you'll be left with negative 1 plus 2, that will be 1 itself. So these two will be equal. Okay. Now let's rewrite it. So this is equal to, so in the first expression I'll do one thing. I'll take 1 by negative 2 common. When I do that, so I'll have 1 divided by 1 minus z by 2 minus of, here you can take minus common, so minus into minus plus 1 by 1 minus z. Okay, see, if mod z is strictly less than 1, then definitely this implies mod z by 2 is also less than 1. There is no doubt in it. Okay, so now I can write expansion for the first one and as well as for the second one. Okay, so let me write the expansions here. So first one is negative 1 by 2 into summation n equal to 0 to infinite. You have z by 2 whole power n plus summation n equal to 0 to infinite, you have z power n. Okay, so this is possible. Why? Because you know mod z is less than 1, and that implies mod z by 2 is also less than 1. So in this region we have these two expansions. So in the first region R0, so f of z can be expressed this way: f of z equal to can do one thing, you can combine those, you can add those two summations. Okay, but let me take one more step. Summation n equal to 0 to infinite. If I take negative 1 by 2 to the inside, so negative 1 by 2 power n plus 1 into z power n plus summation n equal to 0 to infinite, you have z power n. Okay, so you can do term by term addition. So when you do that, you get n equal to 0 to infinite. So you have negative 1 by 2 power n plus 1 minus 1, or plus 1. In other words, let me write it this way: 1 minus 1 by 2 power n plus 1, this multiplied with z power n. So this is the series expansion of f of z when mod z is strictly less than 1. Okay, so we are done with the first region. Now let us move to the second region, that is R1. What is R1? That is the annular region given by 1 less than mod z less than 2. So let us see, try to observe one thing. Here we have mod z is strictly less than 2. See, this implies, I can see one thing, mod z is less than 2, that is fine. Whereas the other inequality, what you have is 1 is less than mod z. So this implies, can I write it this way: 1 by mod z, which is less than 1. Okay, so now I have these two conditions. One is mod z is less than 2, another one is 1 by mod z is less than 1. So now let us start with the function f of z. After writing partial fractions, you'll have 1 by z minus 2 minus 1 by z minus 1. Yeah. So here let us take 2 common, negative 2 common, like earlier. So if I take negative 1 by 2 common, so this is 1 by 1 minus z by 2. Okay, minus, and here you know 1 by mod z is less than 1. So if you have z, then the things will not work. So I should have 1 by z here. So to get 1 by z, let me take 1 by z common. So when I do that, I get 1 by 1 minus 1 by z. Okay. So you know these two things. One thing is mod z by 2, which is less than 1, and modulus of 1 by z, that is also less than 1. So using those two expressions, I can write these expansions. So summation, my negative 1 by 2 summation n equal to 0 to infinite, this is z by 2 whole power n, minus 1 by z summation n equal to 0 to infinite, we can have 1 by z whole power n. Okay, so now therefore the expansion of the given function is nothing but summation n equal to 0 to infinite negative 1 by 2 power n plus 1 into z power n, plus this is the Taylor's expansion, and the other one, that is n equal to 0 to infinite negative 1 by z power n plus 1. So this is the Larn series expansion of the given function in the second region. Okay. So we are done with second region. Let us move to the third region. So now R3, that is the third region, which is nothing but mod z is strictly greater than 2. If mod z is strictly greater than 2, this implies 2 by mod z, this is strictly less than 1, isn't it? And one more thing we can observe, if mod z is greater than 2, this implies, you can say that mod z which is greater than 2, which is also greater than 1, because 2 is greater than 1, no? So this implies I can say mod z is strictly greater than 1. That implies 1 by mod z, this is also less than 1. So now these are the two things you have. 2 by mod z is less than 1 and 1 by mod z is less than 1. So if you want to write expansion in this region, you try to have 2 by z and 1 by z in place of x. So let us see how to do that. So given f of z in partial fractions, 1 by z minus 2 minus 1 by z minus 1. So what shall we do now? I want to get 2 by z. So if you want to obtain 2 by z, you should take z common. So let me take 1 by z common here. So 1 divided by 1 minus 2 by z. Okay, minus. So here I need 1 by z. So here also I'll take 1 by z common. So 1 divided by 1 minus 1 by z. Okay, now we know the expansion separately. Since we know modulus of 2 by z is less than 1 and also modulus of 1 by z is less than 1, we can write the series expansion of these two. So this is 1 by z summation n equal to 0 to infinite 2 by z whole power n minus summation n equal to 0 to infinite, here you have 1 by z, this is 1 upon z whole power n. So finally summation n equal to 0 to infinite, so 2 by z power n plus 1 minus of summation n equal to 1 to infinite 1 by z power n plus 1. Yeah, you can combine. So when
Sir, 2 power n, sir.
What? Z power n plus 1 only,
n,
no?
sir.
Okay, this is 2 power n, correct. So you can combine these two. So this is summation n equal to 0 to infinite 2 power n minus 1 into 1 by z power n plus 1. So this is the series expansion of the given function in R2. I named it as R2, not R3. That is mod z is greater than 2. Okay. Now let us write the power series expansion of the given function in all regions. Let's say if this is the given problem, f of z equal to 1 by z minus 1 into z minus 2. And now let us see what are Larn series expansions. F of z and Larn series expansion about 0. Cheers. So first region, let me write this, f of z equal to what is the first one we saw? Summation n equal to 0 to infinite. First we saw Taylor series expansion, right? And here I wrote, yeah, 1 minus 1 by 2 power n plus 1. So this is 1 minus 1 by 2 power n plus 1 into z power n. This is what valid when mod z is strictly less than 1. And the second one, f of z equal to summation n equal to 0 to infinite this expansion is negative 1 by 2 power n plus 1 into z power n plus summation n equal to 0 to infinite, you have negative 1 by z power n plus 1. So this is the expansion when 1 less than 1 strictly less than mod z less than 2. Okay, and whereas the other guy f of z equal to summation n equal to 0 to infinite, which is nothing but where is it, 2 power n minus 1, okay, which is 2 power n minus 1 into 1 by z power n. Z power n or z power n plus 1. This is what when mod z is greater than 2. Okay, so we got this Larn series expansions of this function in all three regions. You could clearly see what are those regions here. One is mod z strictly less than 1, and another is the region which lies between mod z equal to 1 and mod z equal to 2, and another is the region which lies outside the two circles. So R0, R1, R2. Okay, so if you are asked to write all Larn series expansions, then you should write in every region. It has two singularities, that is why you got three regions. Whereas if it has more than two singularities, let's say if the given function is this, f of z equal to 1 by z into 1 minus z into 2 minus z. Let's assume that this is what you have. Then you see what are the singularities here. 0 is one singularity, 1 and 2. These are the singularities. So when you look at the regions, so about 0 is 1, so another one is between 0 and 1, this is 1, and another one is between 1 and 2 and about 2. It's like this. These are the regions I'll have. One is 0 less than mod z is less than 1, another one is 1 less than mod z less than 2, another one is mod z is greater than 2. But if you observe that all these three things are not fully analytic. Earlier we have a region where the function is fully analytic. I mean, inside that circle there is no singularity in the earlier case. For example, you look at it here, in the region R0, there is no singular point. Okay, but here the center is a singular point. That's the problem. So if you centered at z equal to 0, this is what the regions you will get it. Suppose if you change the center, let's say I'm interested to take the series expansion about z equal to minus 1. About z equal to negative 1. So then the things will change. So first you identify the singularities. 0 is one singularity, and next 1 and next 2. These are the singularities. And when it comes to the center of the circle, this is what? Z equal to negative 1. This is where we'd like to center. Right? So now you draw the regions. So the first region will be this. That's what exactly modulus of z plus 1 is strictly less than 1. The radius of this neighborhood is 1. Okay. So the next, the region between these two. So that's what 1 strictly less than mod z plus 1 less than 2, because this distance is 2. So R0 analytic region, R1 will have both analytic and and the other part as well, the singular part. And next, and this will be R2. So that is what, when 2 less than mod z plus 1, which is less than 3. Okay, so next finally R3. So that is what, mod z plus 1, which is greater than 3. So now here you are going to have 4 Laurent series expansions in these 4 different regions for the same function f of z. Okay. Now let us try other problems, and you do one thing. Will you take this as homework? Only thing, you need to make it as a partial fractions. Do one thing, take it as a homework. First you get its partial fractions. Yeah, it will take time, but keep your time and do it. Okay. If you solve it correctly, then definitely it means you understood this topic and you're confident in it. Okay, so make sure you solve this problem by tomorrow. And do one thing, and before that, let me give you a simple problem. Let's say if you have f of z equal to 1 by z into z plus 3. Okay, find Larn series expansions about z equal to 0. So first you do it, and next you think about this problem. Okay. Now let us look at other expansions. So you know what is the expansion of e power z, and I'd like to mention one thing. You know what are entire functions, right? A function is said to be entire if it is analytic on the entire complex plane. Let's say if f of z is analytic on C, then f is said to be entire function. So you can see some examples. The examples of entire functions are f of z equal to e power z. This is an entire function which is analytic on entire complex plane. And in the second example, Sine Z. And the next example, cos Z. And next, you can take any polynomial function, any nth degree polynomial. Where n belongs to natural numbers. Okay, so these are all examples of entire functions. So now there is something we'd like to make sure about entire functions. So there is a theorem which is called Liouville's theorem, which says that an entire bounded function is constant. An entire bounded function is constant. So let us understand what does it mean. So let us define what is a bounded function in the complex plane first. Let's say f of z is said to be bounded if there exists a m, a real number, moreover positive real number, such that absolute value of f of z, if it is strictly less than m or less than or equal to m for every z belongs to C, then I say such function is bounded function. Okay, So this is the definition for a bounded function on the complex plane. If its absolute value is bounded, if it is bounded above by some number m, then I say it is a bounded function. Now let us write the statement of Liouville's theorem. This is what it says. It says that in an entire bounded function is constant. It means if you take an entire function, its absolute value, it cannot be bounded by some number. For example, you look at e power z. E power z is not going to be bounded. Okay, and sine z. Sine z is also not a bounded function. And don't get confused with the real case. If you take sine z as a function from real numbers, then that is going to be bounded. If the domain is real numbers, then sine z is bounded. But if the domain is complex number plane, then sine z is unbounded function. And of course, earlier we derived what is the absolute value of sine z, which involves sine h square y. Do you remember? So that hyperbolic function makes it unbounded. So keep it in mind, an entire bounded function is constant. It means if you are given that the function is entire, okay, and if you are given that the function is bounded, then definitely that must be a constant function, because there is no entire function there is no non-constant entire function which is bounded. Okay. So I'd like to talk about e power z exponential function. That is an entire function, so that's why I'd like to call this result. We're not going to use this result, but keep it in mind. And we have extension, we have corollary to this theorem. That corollary says, like, if you take a neighborhood around z0, okay, and let's say f is analytic in this neighborhood, and if you come to know that absolute value of f of z is less than or equal to modulus of f of z0, then definitely the function remains constant when you know f is analytic in this neighborhood, and the entire function will be equal to that constant value. Okay. Anyway, this is all leads to other discussion, so let me stick to Larn series expansions here. Now e power z, we know what is its Taylor series expansion, which is summation n equal to 0 to infinite z power n by n factorial. This is what when mod z is less than infinite. It means the radius of convergence of e power z is infinite. Why? Because it is an entire function. Okay. Now from this, I'd like to get what is the expansion of e power 1 by z. What is the expansion of e power 1 by z? Can I simply write this? Summation n equal to 0 to infinite. So in place of z, I need to plug in 1 by z. So 1 by n factorial into 1 by z whole power n. Okay. So if it is true, then what is the validity? Mod z must be, must be less than or equal to 1, or greater than 1, or less than infinite, or greater than 0. What is it? Are you finding it difficult? See, this is simple. All that you need is, this expansion, it is valid for every mod z which is less than infinite, right? Now here we have 1 by z. We know 1 by z is not defined when z equal to 0. So you remove that point. So 0 strictly less than z, mod z, which is less than infinite. So this is the region of validity. 0 less than, mod z less than infinite. Okay. Similarly, we can write some other expansions. So we know the expansion of Sine Z, that is summation n equal to 0 to infinite negative 1 to the power of n, and this is z to the power of 2n plus 1 by 2n plus 1 factorial. Okay, so from this you can see what is sine of 1 by z expansion. Sine of 1 by z, see, we know this expansion is valid when mod z is strictly less than infinite. So sine of 1 by z expansion, that is n equal to 0 to infinite negative 1 to the power of n. This is 1 by or let me write it this way, negative 1 to the power of n by 2n plus 1 factorial into 1 upon z whole power 2n plus 1. And what is the region of validity here? 0 less than, mod z is strictly less than infinite. That's it. Okay, similarly you can think about cos 1 by z, right? These are all. So these are the expansions of e power 1 by z and sine of 1 by z, and you can see the region of validity here. So remember one thing, whenever you write a power series expansion, you should make sure about its region of validity. So the region of validity here is this. Similarly, like earlier also we have seen some expansions. For example, you can take this guy. For this function, this expansion is valid only in this region. It means this expansion will converge us to f of z when mod z is strictly less than 1 only. Okay. Similarly, the second expansion is converges to f of z when mod z value lies between 1 and 2. And the third expansion converges to f of z when mod z is greater than 2. So whenever we write a series expansion, we should make sure about region of validity. That is what we call region of convergence. Sometimes you may be given with a function and some expansion, you will be asked to find the region of convergence and also the radius of convergence. So radius of convergence is easy. What you can do is you can see the distance between the center and the nearest singularity. That will give you the radius of convergence. And the radius of convergence we'll discuss for a Taylor series expansion. But when it comes to Larn series, we'll have annular region. You may talk about the radius of the annular region there. Okay. Right. So in the next class, so we are going to discuss about residues, and we'll classify the singularities based on this Larn series expansion, and we'll find the residues. I hope now itself I can classify the singularities, but anyway, let us start that as a fresh class. Okay, so I'll stop it here for today, and let me know if you have any questions or doubts.